All right, so we've made it essentially to our last case for secants and tangents. And I'd love to say we have a great way to solve these. Honestly, we don't. So the case here is, what do you do if the tangent power is even and the power on secant is odd, right? We kind of said anytime the power on secant is even, you're kind of good to go. That was option number one. If your secant power is odd, but then your tangent power is also odd, then we can do what we did in option two, when you're trying to sort of take one secant and one tangent out and kind of convert the rest into secants. Option three doesn't really have a great technique. You know, in theory, what you're kind of doing here, so your tangent power is even. In theory, what you're doing is you're taking all those tangents. So if it's even, it would be right to the 2, to the 4, to the 6, to the 8. Converting all of those into secants, right, using our Pythagorean identity. Where is it? Tangent squared right would be secant squared x minus 1. So then you just have a whole bunch of secants, and then the move, once you have that, once you have a whole bunch of secants, is essentially to do like a really long and involved integration by parts. However, the words long and involved were just said. So it's surprisingly long. You kind of do a lot of steps, and it gets you just like a surprisingly small amount of progress, and you know, eventually you get to the point where you can kind of keep going and just whittle it away, just like one little bit at a time. That's just kind of too long and a little bit unreasonable for you guys to be doing right now. Essentially what it comes down to is what the book is calling a reduction formula here. So converting everything kind of into secants. So then you're going to have, I guess in theory, right, you know, any kind of even powers here, you'd be getting secant squares. Kind of by definition, the power of the secant here has to be odd, right? So kind of 1, 3, 5, 7, something like that. So plus 2 or you know, plus sort of 2 or 4 or 6, you're still going to have odd powers. So all these guys would be sort of odd powers of secant. And the move here is to use this reduction formula. So, you know, the book has kind of gone through and gotten us a generic version of what these integrals for secant would look like. We're really only going to see secants here to the odd power. If we had them to the even powers, we would kind of just take a secant squared apart, convert the rest to tangents, and we'd be good to go, right? So kind of by definition, by sort of situation, the powers here would be odd. And so what you get here, so secant to the n of x, the integral of just that, is going to end up looking like secant to the n minus 2 of x. So right, if this is 5, then this is 3. If this is 7, then this is 5, right? You're subtracting by 2. So secant to the n minus 2 of x times tangent of x. So that's kind of a secant tangent thing over n minus 1. So right now you're dropping the power by 1 and you're dividing, plus n minus 2, so matches the power here, over n minus 1, matches the denominator here, times the integral of the secant of n minus 2 of x dx. So you get this formula that essentially, you know, it gets you a piece here plus another integral where the power has kind of dropped by 2. This has a little bit of an integration by parts vibe to it, right? I think I've said this right. This comes from a long integration by parts process. And so what it allows you to do here is, so say if you started with secant to the 7, this would get you kind of a secant to the 5 times tangent over 6 plus, you know, 5/6 secant to the 5 of x. And you say, okay, well, great, what do I do with this? And the answer is, well, you run this whole process again. So you could go from 7, right, to kind of 5 and 5, and then from 5 you'd get, right, like a 3 and a 3. From that 3 you would get, right, a secant, and then the integral of a secant to the 1. And then secant, even though it's not something we've seen tons and tons, we did it at some point say there is an integral for just a single secant of x. Let me sort of, let's run through one here just like quickly so you can actually kind of see it working. this just a lot of details here, so it's maybe tricky not to get sort of lost in the lost in it. So say I've got secant cubed of x dx, right? So the idea here is you're going to drop right from 3 to 1. You know, in theory, this is kind of secant to the 1, right? Times tangent over 3 minus 1, right, is 2, plus 1, right? These match. 3 minus 2 is 1 over 2. So these match times the integral of secant, right, to the 3 minus 2. So secant to the 1. Whoops. Oh gosh, that's not really where I wanted it. Secant to the 1 of x. Oh, that's in the wrong spot too. Boy. I had written this out in advance so it would look nice, and then I immediately screw it up. So then you'd say, well, great, okay, so then 1/2 the integral of secant. If you can get to a single secant, the integral of that, right, the antiderivative is the natural log of the absolute value of secant plus tangent x. We kind of had that a little bit as a throwaway in 8.1. We sort of said, oh, let's kind of notice using some natural log techniques, we can get antiderivatives, not just for sine and cosine, but also for secant, cosecant, tangent, and cotangent. We can kind of hit all 6 of them with some of these natural log techniques. So this is like a very kind of everything in the kitchen sink kind of setup. We're really, really digging deep to kind of get this going. So secant cubed would go something like this. You could then kind of extend it and imagine, okay, a secant to the 5, right, would go from a cube to a cube, and then that cube would go from here, right, to a 1 to a 1, and then that last one you could do with this log stuff. You're always going to end up, because kind of by definition, right, we're starting with an odd power on the secant. You're kind of always going to end up with, you know, if you're subtracting by 2 each time, you know, you're going to go, right, 9 to 7 to 5 to 3 to 1. You're always going to end up with something like this. You'll always kind of wrap with this natural log of the absolute of secant plus tangent. So let's take this back then to actually like what we were originally talking about, which so maybe would be something like tangent squared times secant cubed dx. So the move here is pretty simply just like take whatever your tangent power is, right? And you're just going to rewrite tan squared of x, right, should be secant squared x minus 1. So then this integral becomes, right, secant squared x minus 1 times secant cubed x dx. So then this is, right, really the integral of secant to the 5x minus secant cubed x dx. Right, so you're pretty much just like converting this into all secants, kind of, you know, by the way it's set up, by the nature of the setup, they're all going to have odd powers, which is kind of what we were expecting. The integral of secant cubed, we kind of just did that, right? That should be here, right? So that one we know secant to the 5, we'd have to kind of go through this whole process again. So let me see if I can write this out just like quickly. Secant to the 5x, right? So that's going to be what? Secant, so you're dropping it by 2 cubed times tan x over n minus 1, right? So over 4 plus, I can't really have these both, right? So then power matches here, so that's going to be 3 over 4 integral of secant cubed x dx, right? And then in theory, you know, so that's secant to the 5, right? This, you would just use the same thing that we did again, right? From above. So kind of interesting, right? You're just going to get these kind of long strings of things. I don't love this because it kind of is just a formula, and I feel like it's kind of boring to just be like, use this formula. You know, I kind of always like us to actually like, you know, do the work and see what the techniques are. The integration by parts here is just so long. And in theory, once you go through it, you kind of start to see this pattern. So this is semi-decent. Let me see if I can quickly, so just in one line, I'd like to give you guys a final answer here. I kind of screwed up by not leaving myself tons of space. So this is secant to the 5, right? So that was secant cubed of x, tan x over 4, right? So plus 3/4 times what this secant cubed derivative was. Oh, you know what? I should be more clever than this. So the original became secant to the 5th minus secant cubed of x, right? This gets us a 3/4 integral of secant cubed. So this is going to be a 3/4 integral minus an integral of 1. So I guess technically this would be minus 1/4 times the integral of secant cubed. So maybe I'll write that instead, right? Minus 1/4, and then the integral of secant cubed is the process I did up here. So I'm just going to essentially copy and paste this down. So minus 1/4 secant x tan x over 2 plus 1/2 natural log absolute secant x plus tan x, right? And that whole thing is plus big C. So like, oh geez, all right, you could even see it. There we go. So like this whole thing gets out of hand pretty quickly. So I'm probably not going to make you guys do a few of these. You know, maybe they'll end up just as like bonus questions or something in the end. But that's the technique. That's kind of what you use. You use this reduction formulas. I also just want to sort of show you, just so you've seen it. There exist reduction formulas for all 4 of the trig functions. So in a pinch, they're here. You'll kind of have them in the notes as a reference. With all of our different like setups that we've done, you should be able to attack a lot of these different integrals just using those techniques rather than going to the reduction formulas. But they're there. I mean, they'll work, right? These are reduction formulas for kind of individual sine, cosine, tangents, and secants. You know, so those can help you there for sines and cosines. We kind of did those a lot where, you know, if it's an even power, you're using those half angle formulas. If it's an odd power, you're sort of taking one away and you're converting the rest into the other, into sines or cosines or vice versa, right? Different sort of powers of tangent, you would do stuff like, you know, if it's an even one, tangent to the 4 or something, you would be sort of saying, okay, so tangent squared would be, right, a secant squared minus 1. So then you kind of get a secant squared from there and you start to expand it and do some of our regular stuff. In any event, and then of course the sort of secant one is here. So these exist, they're there. You can probably again tell by my tone, I don't really love them, I don't love using them, but they are there, and so I want you guys to see them. I think the book likes them. You know, they're okay, and obviously we kind of need it, especially this last one, the secant one. I wouldn't really expect you guys to use sine, cosine, or tangent too much on what I'm asking you to do, but the secant one you might need. In any event, that's section 8.3. I guess I should also say the strategies for secant and tangent, you can imagine there are essentially kind of matching strategies for pairs of cosecants and cotangents. I'm not going to go through them all, of course, right? You're just kind of flipping around some negatives more or less, but essentially the strategies would be exactly the same. So those exist. I want to acknowledge that those exist. That's the section. So pretty good. Lots of different sort of checklists to go through, a few different techniques. There we have it, section 8.3.